Good day, everyone. Today we will talk about multiple integrals. Multiple integrals can be defined as concept of integration to functions of multiple variables, which allowing the calculation of quantities over multi-dimensional region. It is important to know that the multiple integral can be used in physics, engineering, probability and statistics, and also economics. In this video, we will learn about evaluate double integrals over rectangles and general regions, evaluate triple integrals, and the application of multiple integrals. First, let us come to the double integral over rectangular. As you can see, the basic function of double integral over rectangle is r equal to ab multiple cd, which means xy is a subset of r squared, which means b is larger or equal to x, and x is larger or equal to a, and for d is larger or equal to y, and y is larger or equal to c. ab and cd denotes the Cartesian product of the two closed intervals ab and cd. It consists of rectangular pairs xy such that b is larger or equal to x, and x is larger or equal to a, and also d is larger or equal to y, and y is larger or equal to c. The graph of y represents a surface about the xy plane with equation z equal to fxy, whether z is the height of the surface at the point xy. Let the xs be the solid that lies on r and under the graph of f. As you can see in the figure, shows that the model of the xy function. In solving the question of double integral over rectangle, first of all, we should know how to divide the regions R into smaller rectangles Rij, each of the area and with size x and y. We do this by dividing the interval AB into m subintervals and dividing the interval CD into n subintervals. Hence, x equal to b minus a divided by m, and y equal to d minus c divided by n. And a, the area should be the multiplication of x and y. As you can see, how the separation of the subrectangles in the figure. In order to solve the question, first of all, we need to know how to find the volume of rectangle. The volume of a thin rectangle box above Rij is f xij and yij differentiated by a, whether xij and yij is an arbitrary sample point in each Rij as known in the following figures. Fxy is the height of the corresponding thin rectangular box, and a is the area of each rectangle Ij. Using the same idea for all the subrectangles, we obtain an approximate volume of the solid as shown in the video, and this sum is known as a double Riemann sum and can be used to approximate the value of the volume of the solid. Here, the double sum means that for each subrectangle, we evaluate the function at the chosen point, then multiply by the area of each rectangle, and then add all of the results. In the single variable case, a better approximate can be obtained to the actual volume if m and n becomes larger. So it means that v can equal to limit x and y equal to infinity, which the integration of xij and yij to a, or you can sub another formula like this. Note the sum approach a limit in either cases, and the limit is the volume of the solid with the base r. And now you can see this is the formula that you should done for the solution. The double integral of the function fxy over rectangular region r in the xy plane is defined as like this. And now, after understanding the basic concept, let's come to the example. The question is consider the function z equal to fxy equal to 3x squared minus y over rectangular region R, which is 0, 2, multiple 0, 2, is shown in figure 15.1.4. There are two parts that we need to solve for this example. The part A is set up a double integral for finding the value of the cited volume of the solid S that lies above R and under the graph of F. The second part is divide R into 4 square with m equal to n equal to 2 and choose the sample point as the upper right corner point of each square 1, 1, 2, 1, 1, 2, and 2, 2, which shown in figure 15.1.4 to approximate the cited volume of the solid S that lies above R and under the graph of F. Okay, then you can see this is the solution for the part A, which means the formula of volume. And this was the solution for B. First of all, you should separate the rectangular into subrectangular according to the point given. Afterwards, generate the formula of the volume and solve it, and you will get the answer of 24. Okay, now let us come to double integral over general regions. For double integrals over general regions, it should be able to integrate a function f not just over rectangle but also over region D of more general shape, such as the one illustrated in figure 1. In this subtopic, we propose that D is the bounded region, which means that D can be enclosed in the rectangular region R as in figure 2. Then we define a new function of f with domain of Ry by shown in here fxy, which include the fxy if xy is in D, and if fxy equals to 0 if xy is in R but not in D. And D is the bounded region, but R is the rectangular region. If f is integratable over R, then we define the double integral of R over D by the formula shown here. It makes sense because R is the rectangle, and so R fxy divided by A has been previously defined. Okay, now let's come to type 1 and type 2 regions. First of all, a plane region D is said to be of type 1 if it lies on between the graph of the continuous function of x. That is mean that D equal to xy, which B larger to x and x larger to A, and the G2x larger than y and y larger than the G1x, whether G1 and G2 are continuous on AB. So you can see there are example for the type 1 region. Then let's come to type 2 regions. For type 2 regions, you can consider that plane regions of type 2, which means that if it lies between the graph of two continuous functions of y, which means d equal to xy, which d larger or equal to y, and y larger or equal to c, and the h2y larger or equal to x, and x larger or equal to h1y, whether h1 and h2 are continuously. And you can see that below are the example of type 2 regions. After identifying according to the type of region, now we come to a step of finding the function of solutions. By using the Fubini theorems, for a function fxy that is continuous on a region D of type 1, we will have the integration from start from y, then continue by start of dy, then continue by dx. And similarly, for a function fxy that is continuous on a region D of type 2, we will have the formula of starting integration from dx, after all continue by dy. The mainly difference between these two types is the type 1 is dy dx, and for type 2 is dx dy. Okay, let us go through an example of double integrals over general regions. The question is evaluate double integral d x plus 2y dA, whether d is the region bounded by the parabolas y equal to 2x squared and y equal to 1 plus x squared. So first of all, we need to scratch the bounded region as shown in the right side. The parabolas intersect when 2x squared equal to 1 plus x squared, that is x squared equal to 1, so x equal to plus or minus 1. Since the scattered region is a type 1 region, so the domain should be xy equal to 1 larger or equal to x, or x larger or equal to negative 1, and 1 plus x squared larger than y, and y is larger to 2x squared. The lower boundary is y equal to 2x squared, and the upper boundary is y equal to 1 plus x squared. And now that's the solution. And after the calculation, you will get the result of 32 divided by 15. And that's all for the example of double integral over general regions. And now you can see the additional knowledge for double integral. This is a critical knowledge you should know before starting your solution of double integral functions. But the first knowledge point was fxy dA can be rewritten as fxy dy dx or fxy dx dy. And after the f for the integration process, if your formula were in dy dx, you should start your integration from dy after continue by dx. And at the same point, if your formula was dx dy, you should start your integration from dx, then continue by dy from the integration point which is nearest the functions. This is necessary to follow this form concept if you wanted to score the marks. Now, let us come to triple integral. The triple integral of a function f xyz over a rectangular box B is defined as this equation if the limit is x. In Fubini theorem, if f xyz is continuous on a rectangular box B equal to AB multiple CD multiple EF, then the equation will be shown like this, which is f xyz are integrated by BA dx, dc dy, and fe dz. This integral is also equal to any of the other 5 possible ordering of the iterated triple integrals. And now let us come to the subtopic of identifying the type 1 and type 2 regions for the triple integral. If d in the xy plane is of type 1, as the figure shown below, which means that e equal to xyz, which b larger or equal to x and x larger or equal to a, the g2x larger or equal to y and larger or equal to u1x, and the u2xy is larger or equal to z, u1 and which larger or equal to the u1xy, then this type 1 region, and the formula will be as shown below. And then let us come to the right side for the type 2 region. If d in the xy plane is of type 2 region as the figure shown below, which means that e equal to xyz, which d larger or equal to x larger or equal to c, h2x larger or equal to y larger or equal to h1x, and u2xy larger or equal to u1xy. In this situation, the figure or the region can be defined as type 2 regions, and you can define the function as shown at the bottom of the figure. That's the function for type 2 regions. By comparing these two regions shown, you can clearly see that the difference between type 1 and type 2 region of triple integral. Okay, now let us come to the first example for triple integral. The question wants us to evaluate the triple integral as shown below, which is x plus yz squared, integrate dx, then integrate dy and integrate dz. And these are the solution. You can just directly integrate according to every upper boundary and lower boundary, but you should start from dx, continue by dy, then dz. After all, the final result you will get for this question was 36. Okay, now let us come to the second example. The second example is about the triple integral over rectangle regions. The question wants us to evaluate the triple integral of x of function x to yz dv, whether b equal to xyz, which means 1 larger or equal to x larger equal to minus negative 2, 3 larger equal to y larger equal to 0, and 5 larger equal to z larger equal to 1 as shown in the figure below. The figure below will give us every point of the three-dimensional regions. For this example, you can solve it from starting from dy dx dz or dx dz dy, although the arrangement of the integration step is different, but you will get the same result of 162, and every upper boundary and lower boundary are shown clearly in the question, so you can just directly doing the process of integrations. Okay, now let's talk about the application of multiple integrals. As shown in the monitor, you can see that these are the application of multiple integrals. First, calculating volumes and mass of objects. Second, computing center of mass and standroids. Third, solving physical problems. The fourth application was computer graphic and image processing. Fifth, signal processing. Six, shading and lighting, calculation shading of lighting. Seven, image filtering and convolutions. And the eighth application was anti-aliasing from 2D and 3D. These are the common and popular Newman application of multiple integral. If you're interested in that, you can search it through Google. And that's all for the video today. Thank you.